China's humanoid robots outrun humans in Beijing half marathon, marking major AI leap. Beijing witnessed a stunning glimpse into the future as humanoid robots faced past human runners in a half marathon on Sunday, showcasing China's rapid advancement in artificial intelligence and robotics. Now it's time to go in detail and uncover the full story in today's AI podcast.
I want you to imagine for a second that you're standing right at the finish line of a major international half marathon.
Okay.
You've got your coffee in hand, you're bundled up against that morning chill in Beijing, and, you're just waiting for those elite runners to finally come into view.
Right. The absolute peak athletes.
Exactly. You know the drill. You're expecting to see these peak human athletes, the ones who have literally dedicated their entire lives to optimizing their bodies. They're coming around the final corner. Muscles are straining. Sweat is pouring down their faces. I mean, they are pushing the absolute biological limits of human cardiovascular endurance.
The huge moment.
Yeah, but then the very first figure that actually rounds that corner, it doesn't have sweat pouring down its face.
Yeah, definitely not.
It doesn't even have muscles. It is a humanoid machine, just sprinting past you with this rhythmic, metallic precision to take the win.
Which is just a staggering visual to even think about. I mean, it forces a complete reassessment of what we even consider to be physical competition.
It really does.
We're looking at this really profound indicator of where artificial intelligence and physical robotics are converging right now. And the crazy part is, it's playing out in real time on public streets.
And that convergence, that's exactly our mission for today. We are taking a custom deep dive into this massive stack of recent sources you shared with us, all of them detailing this exact milestone in Beijing, where humanoid robots didn't just compete against humans, they completely shattered expectations.
They absolutely did.
So, okay, let's unpack this. Because to truly grasp the implications of a machine running a half marathon, we have to look really closely at the actual mechanical reality of what just happened on that race course.
Right, because this isn't just a quirky novelty story about a robot running. The underlying physics are what move this totally out of the realm of like a PR stunt and into hard applied science.
Yeah, and the headline detail in your sources, the thing that really jumps out is the raw speed. The winning robot in this Beijing half marathon, which was developed by the Chinese smartphone giant Honor, by the way, it crossed the finish line in 50 minutes and 26 seconds.
Yeah.
50 minutes and 26 seconds.
Which is a time that fundamentally alters the benchmark for bipedal robotics.
Seriously. And just to put that 50-minute mark into perspective for you, that time officially surpassed the human half marathon world record.
Wow.
Yeah, a record that was just set this past March in Lisbon by the Ugandan runner Jacob Kiplimo. So you have a human being at the absolute peak of genetic potential just beaten by a machine.
It's wild. And I mean, we've gotten so used to AI in the digital space, right? Like typing a prompt and watching a beautiful image generate on your screen.
Right, the ChatGPT stuff?
Exactly. But it is a deeply visceral, totally different experience to stand on a real street and watch a physical metal chassis out-endure and outrun a professional human athlete in the real world.
Yeah.
You can literally hear it hitting the pavement.
Just that mechanical pounding.
Yeah. And what's fascinating here is the sheer cascade of mechanical and computational problems that have to be solved simultaneously to make that happen. Because, we see a robot running and we immediately just think of motor speed.
Sure, just bigger motors, faster legs.
Right. But bipedal, running on a public street, is an incredibly unstable physical act. Running, if you really break it down, is essentially a continuously controlled forward fall.
Okay, wait, a controlled fall?
Yeah. The human body handles that fall with tendons and ligaments, right? They act like biological springs, storing and then releasing energy with every single step.
Oh, I see. And I'd imagine replicating that kind of biological shock absorption in a rigid metal frame is just a complete nightmare for engineers.
Oh, it is one of the most notoriously difficult challenges in robotics, because every time that machine's foot leaves the ground, it is technically in free fall. So it has to rely on a concept called inverted pendulum dynamics. The internal sensors have to constantly calculate its center of mass, firing off actuators to make these micro adjustments in literally milliseconds just to maintain balance.
Just to not tip over.
Exactly. And then on top of that, you introduce the impact. Striking the hard pavement thousands of times sends these massive kinetic shock waves right up through the robot's legs.
Which can't be good for the computer inside.
It's terrible for it. Without highly sophisticated series, elastic actuators, which are essentially these complex mechanical springs built directly into the joints to mimic human tendons.
Right.
Without those, the robot would literally vibrate its own internal processors and sensors to pieces within the first mile.
So it's actively dampening the physical shock while simultaneously running these intense calculations just to stay upright?
Exactly.
But surviving the physical impact of a half marathon, I mean, that requires more than just good shock absorbers. It requires an immense continuous output of energy, which really brings up the thermal reality of this achievement, right?
Absolutely. Pushing a heavy metal frame forward at world record speeds for 50 uninterrupted minutes. That requires maximum output from the battery pack and from all those leg motors.
And battery output means heat.
So much heat. In any electrical system, maximum output generates massive amounts of thermal energy.
Yeah.
Think about a data center. You have to use these massive liquid cooling systems and giant fans just to keep AI servers from melting down.
Right.
But you cannot strap a heavy, cumbersome liquid cooling unit onto a bipedal runner.
It would ruin the balance, right?
It would completely throw off the inverted pendulum dynamics we just talked about. So the thermal management required to keep these really dense battery packs and actuators from reaching a state of thermal runaway, using mostly just passive cooling and lightweight heat sinks, is a staggering feat of engineering all on its own.
And all of those internal physics, the heat, the balancing, the shock absorption that's all happening while the robot is dealing with the external world.
Right, because it's not on a treadmill.
Exactly. It's not running in some sterile, perfectly calibrated laboratory environment. It is navigating a public street in Beijing.
Which is huge.
So that requires, what, LiDAR, cameras, real-time processing power, just to read the uneven pavement, right?
Yeah.
To avoid potholes and steer clear of the actual human runners who are sharing the course.
Yeah, it represents a massive leap in what we call embodied AI.
Yeah.
So taking the AI processing power out of the safe, air-conditioned server rack
Yeah.
and forcing it to interact with the chaotic, completely unpredictable variables of the physical world.
The physical world is messy.
Exactly.
Well, the 50-minute record is obviously a technical marvel, but the aspect of these sources that really demands attention is the timeline.
Yes.
Because the physical and computational hurdles you just described, they're immense. And yet the speed at which they are being solved completely defies traditional engineering cycles. So let's rewind the clock for a second. Let's look back just 12 months to the very first edition of this humanoid robot race in 2025.
Right, because the contrast is just stark. The 2025 event was viewed largely as kind of an experimental proof of concept.
Yeah, the sources note that only 20 robots participated last year, and it was plagued by failures.
Lots of awkward moments.
Yeah. Robots were struggling just to stay balanced. A lot of them couldn't even finish the 13-mile course, and the winning robot in that 2025 race took 2 hours and 40 minutes to cross the finish line.
Which is far slower than professional human runners.
Much slower. And now, literally just 1 year later, participation exploded to over 100 robots, and the winning time dropped to 50 minutes. I honestly have to push back a little on the mechanics of this timeline here.
Okay, go for it.
Wait, from 2 hours and 40 minutes of stumbling machines to 50 minutes and beating world records in just 12 months? How is an improvement curve like that even physically possible? Because I understand that software and AI models scale rapidly, you add more data, it gets smarter, but hardware does not scale like that.
That's true. Physics is physics.
Right, you cannot simulate a physical battery melting down or a physical titanium joint snapping under pressure. Machining new parts, testing physical materials, building entirely new manufacturing lines. That stuff takes years. How are they overcoming the physical limitations of hardware iteration to make that kind of jump in 12 months?
If we connect this to the bigger picture, the answer actually lies in how modern robotics completely redefines the relationship between the hardware and the software.
Okay.
Because you're absolutely correct that machining new titanium joints takes a lot of time. But the 12-month quantum leap we are seeing right now isn't primarily because they suddenly invented a magical new battery or some physically flawless motor.
Oh, really?
No. It's because the AI got exponentially better at optimizing the flawed hardware that already exists.
Oh, so the brain is basically learning to compensate for the limitations of the body.
Precisely. They use this incredible process called sim-to-real transfer through the creation of digital twins. So engineers don't have to build a physical metal prototype for every single test anymore?
That would take way too long.
Exactly. Instead, they build a mathematically perfect digital replica of the robot inside a simulation, down to the exact weight of every single screw and the exact friction coefficient of the pavement. Then The AI runs millions of virtual half marathons overnight.
Millions.
Millions.
But wait, the simulation is still sterile, right?
Yeah.
Like, the real world has wind resistance, unexpected slick spots from rain, microscopic variations in the pavement that a computer model might completely miss.
And that right there is what roboticists call the reality gap.
The reality gap.
Yeah. And to solve it, engineers use a technique called domain randomization.
Domain randomization. Okay, what does that actually look like?
Basically, they actively inject chaos into the simulation. So they'll randomly alter the virtual gravity for a few seconds, or they'll suddenly change the friction of the digital floor, or randomly increase the simulated weight of the robot's limbs.
Wow. So they're basically torturing the AI in the simulation.
Kind of. The AI learns not just how to run in perfect sunny conditions, but how to instantly adapt its stride when the physical parameters of the world shift completely unexpectedly.
That's brilliant.
So by the time that software model is actually uploaded into the physical metal robot in Beijing, that brain has essentially lived through thousands of years of running experience.
Oh my gosh.
It knows how to fire an existing, maybe even older motor 40% more efficiently, which saves battery life, which reduces the heat buildup we talked about, allowing last year's hardware to essentially achieve this year's 50-minute time.
Okay, that makes perfect sense now. The software optimization extracts the maximum possible potential from the physical constraints.
Exactly.
And there's another layer to this rapid learning curve that's mentioned in the sources, which is fleet learning. Because these robots aren't just operating as isolated individuals, right?
No, not at all. They operate on a shared neural network architecture.
So, think of it like this. If you have 1 million human runners on a course, and one runner figures out a slightly better way to angle their foot to save energy, only that one runner benefits from that knowledge.
Right, they can't instantly teach everyone else.
But with fleet learning, the moment one robot hits a pothole and successfully calculates the micro adjustments needed to avoid falling over, that exact mathematical solution is instantly uploaded to the cloud and shared.
Instantly.
All 999,999 other robots instantly gain that muscle memory without ever having to step in a pothole themselves.
It creates this vertical curve of improvement. So the jump from 20 failing machines last year to over 100 highly capable machines this year. That means the pool of real-world training data just multiplied massively.
Right.
Every single step taken by those 100 robots in Beijing is currently feeding back into the system, optimizing the models for whatever the next iteration is going to be.
And this hyper-speed evolution, I mean, it is actively being fueled by a massive national strategy. And just to be clear for everyone listening, our goal today is to impartially report on the economic and technological strategies that are outlined in these sources. We are not endorsing any specific political viewpoints or geopolitical ambitions here.
Right. We're just looking at the facts on the ground.
Exactly. We're strictly looking at the data. And the data shows that China has an unambiguous strategy to become a global robotics superpower.
Well, the structural support for this industry over there is vast.
Yeah.
It's combining deep government funding, these massive waves of private investment, and of course the utilization of their unparalleled manufacturing hubs to actually build these complex machines at scale.
And they are leveraging those manufacturing hubs not just for mass production, but for highly visible public spectacles.
Right.
The half marathon is a prime example, right? Using this undeniable physical feat to flex their technological confidence. But the marathon isn't even the most intense example we have in these sources.
No, it really isn't.
Earlier this year, there was a showcase at the famous CCTV Spring Festival Gala. And for context, if you aren't familiar, this is a massive television broadcast that draws hundreds of millions of viewers.
It's a huge cultural event.
Huge. And this showcase featured more than a dozen humanoid robots manufactured by a company called Unitree.
And what's wild there is they bypassed simple locomotion entirely and moved directly into highly complex, synchronized manipulation.
Yes. They were performing synchronized martial arts routines. I'm talking wielding swords, handling staffs, swinging nunchucks. And they were executing these incredibly fast, motion-controlled routines in close proximity to human performers, including children.
Which is terrifying from an engineering standpoint.
Here's where it gets really interesting. Consider the engineering competence required to actually authorize that.
Yeah.
To program a 100-pound metal robot to whip nunchucks around mere feet from human beings on a live national television broadcast?
I mean, the margin for error is absolute zero. None. You are relying on LiDAR, spatial cameras, and force torque sensors located in the robot's joints.
Right.
Those sensors have to calculate the exact weight of the weapon, the momentum of the swing, and the exact proximity of the human performers down to the actual millimeter. Yeah. If a single sensor miscalculates distance, or an actuator just twitches from a minor software bug,
The result is a catastrophe on live TV.
exactly, you do not put an experimental, buggy prototype on that stage. You put a highly refined, deeply reliable product on that stage.
Which is wild.
It is. And this raises an important question. Why take that immense risk? Why use a massive cultural broadcast or a rigorous public half marathon to showcase these machines?
Right, why not just release a press release?
Because these events serve a very specific strategic purpose. They're highly calculated public demonstrations designed to signal to global markets, to investors, and frankly to their own citizens, that humanoid robotics have officially transitioned out of the laboratory phase.
Oh, I see. The public needs to see the reliability before they actually accept the utility.
Precisely. When you show a robot swinging a metal sword, millimeter perfect, next to a child, you are subconsciously telling the public, you can trust the safety of this machine.
Right.
And when you show a robot navigating a chaotic 13-mile marathon route without collapsing, you are saying, this machine possesses the endurance to handle the unpredictability of the real world.
Which brings us to the ultimate application of all this technology. Because the end goal of billions of dollars in research and development isn't to just build a society of robot marathon runners or, mechanical martial artists.
No, those are extreme stress tests.
Right. The underlying technology required to achieve those extreme feats is exactly the same technology needed for everyday, real-world utility.
The extreme environment forces the development of incredibly reliable mechanisms for mundane applications. It is a direct translation of generalized skills.
And the sources actually outline the major sectors where experts anticipate immediate deployment. We're looking at factory assembly, obviously logistics and delivery, elder care, security services, hazardous rescue missions, and even just household assistance.
Yeah, and the sources also note that many of these applications are already actively being tested across industrial sectors in China right now.
Wow.
Because the generalization of the AI model means you don't have to build a completely different robot from scratch for each specific task. You're building a foundational physics engine that just fundamentally understands how to interact with gravity and objects.
So what does this all mean? Let's bring this abstract technology right to your front door. The hyper-advanced inverted pendulum dynamics and the real-time pathfinding required to run 13 miles on a crowded street.
Yeah.
That is the exact same underlying technology that will allow a robot to carry a heavy shifting box of groceries up your uneven front steps in the rain without losing its balance.
Exactly. And the force torque sensors and millimeter spatial awareness required to swing a sword safely at the gala. That translates directly to the delicate force control required to have a robot carefully lift an elderly patient out of a hospital bed. Or assist them into a wheelchair, applying exactly the right amount of pressure without causing any injury.
So if the machine can calculate the momentum of a swinging weapon, it can safely and reliably chop vegetables on your kitchen counter.
Yeah.
If it has the thermal management to outrun a professional human athlete, it can easily patrol a massive warehouse for a 12-hour shift or rush into a burning building to execute a rescue without its internal systems just melting down.
Synthesizing the speed of this development, the rapid sim-to-real learning loops, and that strategic public signaling we talked about, the core takeaway for these sources is very clear.
Yeah.
The fundamental question surrounding physical robotics has shifted entirely. It is no longer a theoretical debate about whether robots can replicate complex human physical capabilities. The half marathon answered that.
Unambiguously.
The operative question now is simply how soon these scaled manufacturing hubs will begin deploying them into our homes and workplaces.
We are looking at a vanishing runway between a cutting-edge prototype and mass commercial deployment.
The timeline just forces us to continually update our assumptions about the pace of physical automation. It's moving faster than we thought.
It is a remarkable progression to analyze. Just looking at this 12-month window, from clumsy, unstable machines taking nearly 3 hours to cross a finish line to deeply optimized world record-breaking platforms utilizing fleet learning and digital twins to just sprint past elite athletes.
It's wild.
It is an engineering reality that is rapidly pulling concepts we previously reserved purely for science fiction directly into our tangible reality.
Absolutely.
I want to thank you for bringing these incredible sources to the table and joining us on this deep dive today, because exploring the mechanical how and the why behind these headlines completely changes the way you view the entire technological landscape.
It's been great digging into it.
But before we wrap up, I do want to leave you with one final thought to ponder on your own, building on the reality of that Beijing race. We've spent our time today analyzing the engineering breakthroughs, the thermal management, and what all this means for industrial automation and our daily routines.
Right, the practical stuff.
But consider the philosophical shift for a moment. If a humanoid machine, machined in a factory and trained overnight in a simulated digital environment, can now casually shatter a world record that represents the absolute pinnacle of human physical dedication, pain, and triumph, how will we redefine the intrinsic value and the cultural meaning of human athletic achievement in the years to come?
Okay, one question for you. How did China's humanoid robots improve so dramatically in just 1 year, going from struggling to finish the Beijing half marathon in 2025 to outrunning human runners and setting record breaking times in 2026? Don't forget to comment it. Thanks.